After almost 3 months of learning calculus, I always ask myself, why do we need to know the knowledge of calculus? How can we use it in the real world and solve real issues? The math portfolio becomes a perfect opportunity to test out some ideas I have in mind, but never get the chance to put into practice. In the following video, I'm going to try to conduct 3 real-world problems and solve them on the beautiful Baylor campus. These problems can really show my learning ability and test out if I have known them well. I'm in front of the Probasco Academic Center. The light on the door casts a shadow on the ground. I'm 1.83 meters tall, and the light is roughly 3 meters above the ground. While I'm walking at a rate of 1 meters per second for 3 seconds, 1, 2, 3. At this moment, at what rate is the length of my shadow moving? Different from the questions in the textbook, the ground in front of the new building is not completely flat, and the light is not directly above me. Therefore, I'm not walking the same direction with the shadow. So how will this influence the way I solve this problem? First, I realized the angle will not influence the way I solve this problem, since the light and I still form 2 similar triangles, which means the length of my shadow and my distance from the light is still proportional relating to the height of the person in the light. If I started 1 meter away from the light and start walking while making sure this is the right angle, the distance is velocity times time. At this moment, the blue line is the square root of 1 plus vt squared. Take s as the length of my shadow. Therefore, my height over the height of the lights equals s over s plus the square root of 1 plus vt squared. After some computation, dl dt is 1.182 meters per second, and this is the rate of change of my shadow. Storm very often attack Chattanooga. The trees on campus are very likely to fall down after a strong wind. One solution to prevent this from happening is to attach a wire from the tip of the trees to the bottom of the stake. The height of the small tree is 5 meters, and the height of the tall tree is 7 meters. The distance between these 2 trees are 8 meters. And I decide to place the stake anywhere between these 2 trees. In order to minimize the amount of wire I use, where should I place the stake? The interesting thing here is that there is a 1.5 meters pathway between the trees. The distances to the trees from the pathway are 2 meters and 4.5 meters. Obviously, we cannot place the stake on the pathway. So where should we place the stake? First, let's take the distance from the stake to the tall tree as x. The length of the wire is y, and the distance to the small tree is 8 minus x. Therefore, we get the function y equals the square root of x squared plus 49 plus the square root of 8 minus x plus 25. However, since we cannot place the stake on the pathway, the interval for x is 0 to 2 and 3.5 to 8. dy dx equals 1/2 times 1 over the square root of x squared plus 49 times 2x minus 1/2 times 1 over the square root of 8 minus x squared plus 25 times 16 minus 2x. Let's type it into the calculator. There is a turning point when x equals 4.67. Using candidate test, the smallest y is when x equals 4.69 and y is 14.42. There are some data in the real world that have a relationship that fits a straight line, but aren't exactly linear. The weight of a person and how much weight to put for front squat is one of the relationship like this. And I think it will be really meaningful to find the best fitting line to all this point using calculus, so that we can predict where the next point will be. And now, let's go and collect some data. Sam, how much do you weigh?
175.
And how much do you put for front squat?
135. How much do I weigh?
Yeah.
160 pounds. Front squat?
Yeah.
285.
120 pounds. 95.
145. 135. 113. 80 pounds. 150. 180.
Weigh 160. 100. 110.
120, 60.
120. About 100 pounds.
Okay.
After collecting all the data, I graph them on the scattered plot. In order to find the best fitting line, we need to minimize the sum of the distance from all the points to the line. Instead of getting the perpendicular distance, I decide to find the distance from the point to a point on the line with the same x value. Therefore, the formula will be the sum of absolute value of yi minus kxi plus b. Yi is the y value of the original point. Kxi plus b is the point on the line with the same x value. In order to find k and b, we only need to let the derivative of this formula equal 0. After doing some researches and practices, I get to know this method is called the least squares regression line. I can simply type in all the data into the calculator and it will give me the answer. Therefore, I get k equals 2.009 and b equals negative 162.479. The equation is y equals 2.009x minus 162.479.
Why can't we just get over ourselves?
Being able to solve calculus problems in my daily life, I find the purpose for studying calculus and keep reminding myself these knowledge are going to somehow help me resolve my problems in the future.
They don't mean nothing compared to you.